Okay, so in the previous example, we looked at the sphere and we saw that it was actually quite easy to set up the integral using either either part of the equation that pops up in the divergence theorem. Here's an example which is different. So for this one, we're finding the flux of this fairly straightforward vector field out of the unit cube, which is where all x, y, and z each have their coordinates between 0 and 1. So the reason why this one is not the same is that it's easy to set up an integral over the cube, but it's annoying to set up 6 surface integrals over each face of the cube, right? So we don't want to do that. So the flux coming out of this guy here, this is going to be over the boundary of the cube. So the flux would be the normal component integrated with respect to ds. But we're going to convert this into the triple integral over the cube of the divergence of f with respect to volume. And so this is going to be in parameters from 0 to 1, 0 to 1, 0 to 1. And we're just setting up in Cartesian here. So the divergence then, so the derivative of xy with respect to x is y. Derivative of yz with respect to y is z, and the derivative of xz with respect to z is x. So there's our divergence, and then this is, and well, by symmetry you can actually like write this in whatever stinking order you want. So whatever, dx, dy, dz. It's a nice simple one. Okay, so then let's see, this is going to be, so by linearity of the integral, I can pop this apart into, triple integral over x dx, dy, dz, plus the triple integral over y, plus the triple integral of z. But if you look at these are all the same by symmetry. So I can just skip straight to calling it 3 times. And then what do I have? Well, I've got an integral from 0 to 1 dz times an integral from 0 to 1 dy times an integral from 0 to 1 x dx. So I chose to go with this one here because each of these is going to end up having the same value as this first one. Okay, so then let's see, so I'm going to get 3 times, and then when we integrate, we'll get z evaluated from 1 to 0 is 1. And then the same for this one. And then for this one, we'll get an x squared over 2, which will give us a 1/2. And so we get 3 over 2, which is a lot nicer than having to set up 6 dumb surface integrals.